Please welcome our next speaker, Aditi Gupta, Solution Architect, Worldwide Public Sector, AWS, to the stage.
Hello, everyone. Good afternoon once again. And I'm Aditi Gupta, Solutions Architect, for those who know me already. I see people are still trickling in, but that's OK. Along with me today, I have my customer, Chichuan, who is from GIS. And maybe let's start. Let's wait for people. It's OK, but let's start. So my topic today is about 100 billion data points. Well, actually, that was an old number. Now it has increased, and Chichuan will talk about it. But it's 100 billion data points using AWS Lambda, which is our serverless service. So as you know that we are very customer-focused, here I start with customers, our customers who have been using and succeeding with our serverless services there. So some of our customers are Airbnb, we have AirAsia, we have Discovery. But I'm not going to talk about all of them today. Since I have Chichuan with me from GIS, that is our focus today, Genome Institute of Singapore. So Chichuan.
Good afternoon, everyone. So we are a research institute from the Agency for Science and Technology Research. We do, well, genomics.
Genomics. So,
yeah, genomics.
Sorry, I'm a techie. I don't really understand what is genomics here.
I'll try.
OK.
So say all of us here, human, hopefully. So we have cells, yeah? So you look at our cells, you see a nucleus. If you look into that nucleus, you see chromosomes. If you peek in that chromosome, you find DNA. So what is DNA? That's basically 4 compounds or bases, adenine, thymine, guanine, and cytosine. And we label them using that first letter. So a human typically has about 3 billion base pairs.
3 billion
Yep.
per human?
Yeah.
So that means in this room, currently, we have about probably 30 billion?
That's one way to put it, sure. So collectively, that's your genome, hence genomics, right? And the bases are essentially like, so if you're a book, then the bases are basically the letters which we write the book from. So what can we do with genomics? With genomics, we can infer maybe the color of your hair. We can have a pretty good estimate of your height. And with your genome, I can tell if you are really you and not a pot of cactus, for example. So that's all good. But why are we studying genomics? Because genomics is a very powerful tool for good. I'll just give you some examples of what we do at GIS. So for example, by studying the genomics of pathogens, we have helped decision makers make better decisions to manage serious outbreaks. But it's not just about that. We also improve lives. So our faculty have worked with clinicians to devise better diagnostics for kids with rare disease. And right now, we're working with doctors to devise a way to provide customized, precise treatment for every individual. So this is what we do, right? And I guess you could ask, so why are we here, right? So is there a problem statement? Unfortunately, there is one. So we have too much data. So this graph that you see here on the screen, that shows the cost of producing 1 million bases over the years. Now, if you look at the top line, the solid slope, that's what the cost would have been if genomics technology would track most loss, which basically means if we were to double our capacity once every 2 years. Now, and the dots that you see below that, that's what actually happened. So as you can see very clearly, from the year around 07-ish, the curve just nosedive. So what that means is, it's really, really cheap to produce lots of data. Does this sound like a problem? No? OK. So what does that mean for us? In 2010, we were producing slightly shy of 30 billion bases per day. But as of last year, we broke through the trillion mark. Now, bear in mind, this is a trillion bases, whereby every single one of them has to be examined, they have to be transformed, analyzed, and stored.
Wow.
So imagine, more than 40 times increase. Do you want to guess how much budget did our IT increase by? No, don't bother. Okay, so needless to say, we can't keep up.
So is that how your journey with AWS started?
Yeah, pretty much.
Would you like to share some more on how did you get started? What were your initial workloads there? How did you do it?
Sure. So at the beginning, we were like everyone else. We just tried to replicate our IT on Amazon. That's easy, right? Buy a bunch of buckets, EBS, and what have you, lots of VMs. Just by doing that, we got infinite capacity. And waste, sure, but that was good. But what was interesting was that every single user got full control. So every single user who spins up some assets on Amazon can do anything they want. And this is something that was just not possible previously using on-prem systems.
Okay. So how was the experience there using AWS?
So it was great. I mean, like I said, infinite capacity, right? But it wasn't quite enough for a bunch of us. I'm one of them. So this bunch of us within GIS that we are trying to build fairly complex analytics and data pipelines. So imagine each of these workflows use about dozens or more software tools, and we want to apply them on very massive data sets. Say this is just one example. This is real, by the way. It's not make-up numbers. So it's like each of them have an input size of 100 gig, multiplied by 10,000 samples, multiplied by the number of analytics that we want to run. So you do the math. That's big. And of course, given this size, it has to be automated. I can't click 10,000 times, right? I can't keep track of 10,000 pipelines. So as you imagine, it's complex. It's hard. It's really hard. There's too much IT, too much infrastructure, even if it's on Amazon.
OK, so how did you solve that problem?
Right. So we don't want to do IT, so throw away all the servers. We decided to go serverless.
Going serverless?
Yes, serverless. You know, I think you should take this. Why don't you explain what serverless is?
You put the hard questions to me, OK? Well, OK, since I am on the spotlight, so why not? So what is serverless? Serverless is build and run applications without bothering about the servers. Serverless also means that you get flexible scaling because you're really getting them on demand when you need. You get high availability because this is all taken care of for you by AWS, where all the underlying infrastructure, how many instances to launch, and what is the right capacities, again, taken care of by us. Since there are no servers, it is really launched on demand. There is no idle capacity. You're really spinning out what you need. So this is what serverless is. We do have a couple of services there which can go serverless, Lambda. You have the batch. Let's understand from Chichuan. So Chichuan, which service did you use to go serverless?
Right. So we started off this thing, the AWS Lambda. So what we did was we took one of our pipelines, a variant calling pipeline, we rewrote it in Lambda functions. And it's really pretty simple. It's a very simple setup, right? So we take a sample, drop it into a bucket, and that fires off Lambda functions repeatedly, massively, and at the end of it, we look at it for output. That's it, done. So imagine, it's great because it's event-driven. It's highly performant because it can scale, it just exploits the native inherent data parallelism that our samples have. So you can imagine, in our context, it's essentially unlimited in terms of scale. And no IT, because, draw a bucket, run functions, done. So that was great. It almost seems perfect. Almost. Yes. Almost. But, before that, maybe you can just go us a little bit more about Lambda.
OK, cool. Sure. Let me tell about Lambda's advantages first. So with Lambda, you can bring your own code. The Lambda itself is a function. You can treat it as a function as a service, where there is an event which triggers the Lambda function. The Lambda contains certain functional code which can be executed based on the triggered event, and then it takes certain action, again, whatever has been configured. Now, with Lambda, you can bring your own code. It supports multiple languages like Node.js, Python, Java. You can bring even your own libraries, even the native ones. You could be authoring functions on with the what you get editor, or you could be bringing your own zip files and using them there. It follows pretty simple resource model because you can choose the power rating from 128 MB to a few GB or up to 3 GB. And the network and CPU is proportionately allocated to you. But do remember that Lambda is stateless. So what that means is, because it is just spinned out on demand, if you have to communicate between different Lambda functions, you need to have some kind of either a relational database service or something to keep track of the different state that you might want to configure between different Lambda functions. There is no affinity after the Lambda shuts down. There is no affinity to the underlying infrastructure. The programming model is pretty simple. You can use your processes, threads, your sockets pretty much as usual, like you do with any other programming. And there is built-in SDK using Python or your Node.js. So again, looks pretty simple, pretty seamless. All this is with very flexible use, so you could have synchronous or asynchronous programming there, and it is seamlessly integrated with other AWS services like your S3, DynamoDB, your notification engine, and a lot more. So let's understand, like I explained, that there are 3 components to it: the event trigger, then the function, and the action itself. Let's see, one of the most common questions that comes to me is, what are the possible triggers that you could have? So as I said, it is natively integrated with many AWS services. So on one side, we have data stores like your Amazon S3, DynamoDB. An example there could be that if a file is uploaded on S3, then it triggers a Lambda function to take a certain action. The action could be simply sending a notification. It could be updating. It could be doing some analysis and updating, let's say, a database table. It could be just writing another pre-processing and writing it back to S3, whatever. It's about what is being triggered. So that could be one. Or think of it as Amazon DynamoDB. Let's say when a row is updated, you want to go and update certain other functions. So that, again, can be taken care of by your Lambda. So the triggers could be multiple there from your different data stores, your different endpoints. Like, think of it that you have a microservices architecture where you're running or publishing your APIs using the API gateway. Again, instead of having servers responding to those APIs, what you could have is a Lambda function listening to that particular API and responding to it. It's a trigger as well. There could be AWS step functions that could be running Lambda in the background. And of course, Alexa, our famous Alexa that we have. Similarly, we have different development and management tools, or there are different event and management services which could be integrated with your Lambda. Now, at all points, we know that security is always very important. And when I'm talking of no servers, how exactly I'm really looking at the security of this serverless infrastructure there. So security is always the primary objective at AWS. What we give is very fine-grained controls for both invocation and execution. So you have the function policies where you say that what can invoke the Lambda function. Now notice that what is taken care of by the role, which another program can assume. It could be an application which is assuming that role to say that, yes, it is allowed, it has been given permission to access the Lambda function and execute it. Second, you have the execution roles, where you can see what is it that the Lambda function itself can access. Can it access a certain database? Can it access a certain file system? Is it allowed to send a certain notification? So you have both kind of access, which is given functional policies, as well as execution roles. Now let's understand from Chichuan, what was his experience with this seemingly perfect service out there?
Right. Not so good, actually. So we actually hit the wall with Lambda. Okay. For a start, you have to port your tools into Lambda functions. So imagine you having to do that for dozens of tools every single pipeline. That's too hard. And then there's the faults. It's actually pretty tedious to handle the faults when you're running applications which are really intensive in terms of memory and I/O requirements. So yeah.
Did you use X-Ray by then?
X-Ray. The new service, right?
Yeah.
No, but even if it did get that out of the way, there's still a matter of cost. So for our scale, the free tier goes away really, really quickly. And if you're not careful about planning, the cost ramps up really, really fast. So for folks like us, we have to do the maths pretty carefully. So it's not such a good solution.
OK, so again, how did you solve this problem then?
Well, Lambda didn't work, but we still believe in serverless. We believe we're on the right track, maybe not the right tool. So we tried again. This time around, though, we decided to focus on a different tool. So here comes the AWS Batch. So Batch is a very different tool in a sense. For a start, no functions. Instead, we have containers. And so instead of trying to port your tools into a different framework, what you do is you take your tools and all the dependencies and everything that comes with it, and you put them into a container like Docker, for instance, right? So that's good because that means it's just a one-time effort to package our tools, and then we're done, right? That's easy. And Batch has a very nice ability to play nice with third-party tools, the orchestration tools. For example, in our case, we are using Nextflow. So this is important because remember why I said we are running complex workflows, right? So we are very much relying on such tools to help us orchestrate the process. And last of all, again, no IT, no service, no network to manage. So that's great. So we like it a lot. Before I continue, I suppose you want to talk about Batch.
Sure, why not? So before I tell you about AWS Batch, I would like to tell you what exactly is batch computing that Chichuan is talking about. Before I tell that, I just want to re-emphasize on what is going on here. So we talked about the scale here. Like we spoke about 100 billion data points, which are now a passe. It's 1.3 trillion data points that we were talking of here. And also all the services that we went through, like they went through EC2 instances, which should have been good in most cases. But given the scale that GIS has, then it makes things a little different. Same way for Lambda. That while in itself, and for most cases, it is working out perfect, but for GIS specifically, it was different. So let's talk about batch to understand what it is and how did it solve the problem for GIS. Now, what is batch computing? Batch computing is where you run your jobs asynchronously and automatically across one or more computers. Now, the jobs may have dependencies, making sequencing and scheduling of multiple jobs complex and challenging, which is exactly what sounds like GIS to me. Now, that is exactly where your AWS Batch comes into picture. So let's look at the features of AWS Batch. AWS Batch is a fully managed service. So once again, if you remember from my morning session, what is a managed service? A managed service is where we take care of all the underlying infrastructure for you, from provisioning to installing to managing the servers to managing the HA and everything essentially underneath. So we provision, manage, and scale your infrastructure as per the requirements. At the same time, it is integrated with AWS core services natively. So you can easily and securely interact with services like S3, DynamoDB, and many more which you can think of. Plus, it is, again, cost-optimized resource provisioning. What that means is it will automatically provision the EC2 or Spot instances based on your requirements, whatever the workload says. When I'm saying it verbally, it's not really kind of sinking in to me itself. I cannot really picturize what I'm saying. So let me show you a small video on what actually happens and how does it actually work. What we have in front of you is a overview of how typically a group of workflows look like when we are talking of something like genomics kind of workflow. There are multiple vertical workflows that we are. So the workflows are divided vertically, and there are sequence of tasks that need to be done. The red ones are indicating the compute-intensive workloads, and the green and blue are indicating the memory-intensive workloads. An on-demand compute environment is created, where the min and max instances are given to you. The type is optimal, where it gives you that you can choose the optimal instances accordingly. The jobs are scheduled in a high-priority job queue. As it is to be executed in sequence, the compute-optimized resources C4 are launched. We see that the first few instances are being executed, while there are no other memory-optimized R4 which are still R3s which are still this thing. As the first few compute instances, compute tasks are getting done, we see the R3 instances getting launched and completing. At the same time, there is a compute environment, which is for spot instances. Low priority tasks are being added to Q2. It is saying that bid prices, it is observing bid price less than 25% of on demand. So you see that the low priority tasks are getting executed at spot environment. Now it looks counterintuitive when you have the low cost spot instances running. So it pulls the compute intensive tasks from higher priority queue and delivers it to the spot environment. As we see that the spot environment is completing the tasks, all the red tasks are getting completed. You will notice that the yellow tasks from lower priority are getting picked up. Also, you will notice that in the above on-demand environment, the C4 instances are now automatically getting shut down as the tasks are being finished. You will also see that the R3s are still running based on the maximum which were given to it. And as these will start completing, these will be submitted to your completed jobs as well. Your spot pricing, as you can see on the parameter, is still very much below the bid price. So it is continuing, but you will see if it goes above the bid price, the queuing stops. So this gives you a very quick overview of how it runs and how the instances automatically are provisioned and stopped. Let us go back to GIS and understand from them that how they have been using Batch and what are they doing with it.
Right, so like I said, that worked pretty well for us. And we have since applied it to quite a number of projects. So the one you see on the screen, this is just one such example. So this is what we call a fairly large-scale brilliant calling pipeline. Now, just to assure you that it's complicated, if you look at the lower left quadrant, you see that spider web there. Yeah, that's the actual workflow. So that's what we're doing per sample. So we take that workflow, we multiply it by 10,000 times, and when we do it pretty much anytime we want, over multiple instances, and this is all done automatically. And we didn't have to do anything. We just basically say fire and go. So it was really, really well for us.
That sounds great. So, but Chichuan, what was the impact on the GIS itself for this kind of workload? Right.
So, well, it's good to ask. So this, again, go back to the workflow slide. Well, not the workflow slide, but the workflow that I just talked about. That actually comes from one particular project, which we call the SG10K, which, let's see if I can explain it. Well, to put simply, it's basically trying to build a genomics profile of Singaporeans, literally all Singaporeans. So it's a fairly big project. We're doing a study of more than 10,000 Singaporeans. And as you can imagine, this is pretty massive. The data set goes up to petabyte scale, like literally. When we talk about this project, we don't count in hundreds of terabytes. We say we are now on 1 petabyte, 1.5 petabytes, or 2 petabytes. This is our units of calculation right now. And so imagine running any kind of analysis on such a data set. It doesn't matter what kind of analysis you want to run. It takes effort to plan, right? On an on-prem system, on a shared system, you need to give them heads up. You need to talk to people, and this, just to be able to run something on such data sets. And this takes days or even weeks. But when we use Batch, we found that the lead time becomes negligible. So we can basically just run. So we can run whatever we want, whenever we want. So that was great.
So basically, you're telling me that now that you have capacity, you have the simplicity. Mm-hmm. Is it creating new opportunities for you?
So sorry, let me just try to rephrase that. So maybe you are trying to ask if the use of cloud is fundamentally changing the way we look at problems.
Yeah, you put it better.
I believe so. So maybe I can illustrate that with something that's something of a work in progress. So we know public sector Singapore, so we are fantastic in infrastructure. Yeah? This is what we're really, truly famous for. So let's take an example. Dengue monitoring. So since the year 2006, we've been checking all normal residential buildings once every 3 months. That's easily 1 million inspections per year. We've been doing this for more than 10 years now. So this just gives you the sense of the kind of impressive infrastructure we're sitting on. What if, for every single of those inspections, we find a way to piggyback genomics surveillance? Basically, what I'm trying to say is, we can use existing technology to get genomics information from each and every of those inspections. And we cover that with cloud. So what can I be? Maybe just, what would that be like? Serverless, event-driven, massive scale. And this will give us the kind of data resolution that's, well, something that we have never had before. And we will be able to do things, really cool stuff like real-time outbreak monitoring.
Wow.
And I'm saying that not because this is like the hard problem, because with that kind of data resolution, real-time outbreak monitoring surveillance becomes easy, which is incredible. So this is literally fundamentally changing the way we look at problems. Something that was not before, that was impossible, now becomes easy, becomes a low-hanging fruit. But this is not even close to capturing the kind of possibilities that we can do with this kind of scale. If I were to try to sort of squeeze all that possibility into a single slide, I would choose this one. This is something that we should be very familiar with. We are public sector here, after all. Many smart ideas, one smart nation, enabled by genomics.
Great. That sounds great. Thank you so much for sharing that with us. I'm very excited to see, I'm very delighted to see what all changes we are seeing and how we are contributing in GIS, and very excited to see what other products come up and what other projects come up at GIS. So thank you for that.
Thank you.
I want to make a small correction, though. When I was estimating, I estimated it 30 billion. Well, it's not really 30 billion. Probably it's 600 billion here in the room, which is quite huge already. So great. But thank you so much for sharing your experiences and your time. Yeah. Please do help to fill us the feedback, and thank you so much for joining the session.